I want to continue our study of spherical charge distributions by finishing with this example of an insulating sphere of radius capital R, for which the charge density is non-uniform. In fact, we'll say the density of charge is getting less and less as we work our way from the center out toward the surface. And you can see that the way the diagram is drawn, right? By the amount of shading, it shows that there's a greater density of charge at the center, and it's becoming less and less toward the edge. Maybe such that it would be expressed as rho is equal to, how about just some constant c times the quantity capital R minus lowercase r. So let's see, just as an example, what if we're talking about the density of charge at the very surface where lowercase r is equal to capital R? Then we get rho equals 0. So we're basically saying there's 0 density of charge at the surface. Now at the very center, when r equals 0, then we get rho is equal to some constant times capital R. We can call that rho naught, the density at the center. So anyway, that's what we mean by this expression. It's just a way of saying that the density of charge is getting less and less as we work our way from the center out to the edge. Again, density at the center is this constant c times the radius r, and the charge density at the surface is equal to 0. Well, if that's the case, then I want to ask the same question as in the previous videos. What's the electric potential at point A? What's the electric potential at the surface, which we'll call point B? Might help to draw in our radial axis. What's the electric potential at point C? And what's the electric potential infinitely far away? Now let's do something different here. Let's make a frame of reference. It's not so typical. Most often we'll set a frame of reference where you say v equals 0 at r equals infinity. Once in a while, for spherical distributions, we might want to say that v equals 0 at the center. We can also make this less typical choice to say v equals 0 at the surface. Let's go with that. So then to find the electric potential at the center, we say that VA minus VB is equal to negative the integral, a path that takes us from B to A, the product of E dot dr. Okay, so because we're talking about the difference between A and B, then the electric field we're talking about here is E in, not E out. All right, and we know that E out is just going to be equal to K capital Q over R squared, right? Whether the sphere is plastic or metal, hollow or solid, insulating or conducting, it doesn't matter. At points outside, this is always the expression for the electric field. The electric field inside is what varies, whether this is plastic or metal, hollow or solid, uniform, non-uniform, etc. Okay, so we're going to have to use Gauss's law to figure out what's the electric field at points inside. So let's just choose some random point. We'll call that x. Make a Gaussian surface. It's also in the shape of the sphere. So the integral of E dot dA is equal to Q in over epsilon naught. Now because we chose a sphere, the electric field is going to be uniform, and we can also get rid of the vector notation because the area vectors and the electric field lines are going to be parallel at all points. So both of those suggest that we just get E times the total surface integral for the area of our Gaussian surface is equal to Q in over epsilon naught. Now, we can't say that Q in over V Gauss is the same thing as all the Q over V total. That would suggest that the density is uniform, or that rho is constant, but it isn't. So we can't make that statement. But we can certainly say that whatever rho happens to be equal to, it's just found by taking dq over dv. So the amount of charge inside of our Gaussian surface can be found by summing up rho dv from 0 to, well, gosh, if we wanted to find the charge of the whole sphere, we can say capital Q is rho dv as we go from r equals 0 up to capital R. But if we cut our integration short, if we only sum up for all the charge density from 0 to lowercase r, then we'll say we've only found the amount of charge that lies inside the Gaussian surface. Okay, so there we go. This is the integral of rho dv from 0 to lowercase r, all of that over epsilon naught. So E times 4 pi r squared is equal to the integral from 0 to r of, take our given expression for rho, okay, so E is equal to 1 over 4 pi epsilon naught, 1 over r squared, so I'm just moving 4 pi and r squared to the other side of the equation. We'll cross multiplying. Times the integral of, oops, I got the rho, I haven't written out the dv here. Okay, so dv is the same thing as 4 pi r squared dr. Okay, so we're just going to distribute here. We have cr 4 pi r squared dr minus the integral of c lowercase r cubed 4 pi dr. And the c, the r, the 4, the pi all come out of the integral. That's nice. That means that the 4 pi here cancels with the 4 pi here and here. So we have E is equal to c over epsilon naught r squared. So we got the c both here and here, epsilon r squared. Okay, and then times the integral from 0 to r of r squared dr minus the integral from 0 to r of r cubed dr. And then we can distribute here. E is equal to c over epsilon naught times r over 3 minus r squared over 4. There you have it. That's an expression for the electric field at points inside of this spherical distribution of charge. And so that's what we use for E in as we perform this integral as a way of finding the electric potential at the center. Now, remember, what's the electric potential of the surface? Well, we just arbitrarily chose to let that equal 0. So the electric potential at the center of this non-uniform plastic sphere is equal to negative the integral from capital R to 0 of c over epsilon naught r over 3 minus r squared over 4 dr. I'm really saying VA minus VB. VB is 0. And so I've just dropped the subscript A. And so we're integrating from the surface to the center, right? from B to A. So we flip our limits of integration, change this from a negative to a positive by changing this from 0 to capital R. So the electric potential at the center is equal to C over epsilon naught times the integral of R over 3dr minus the integral of R squared over 4 dr. Okay, so the integral of R is 1/2 R squared, so we get 1/6 capital R squared, right? Pull out the 1/3, and then we get another 1/2 by integrating. You know what I'm saying. Minus, okay, so we're going to get rid of this, pull out a 1/4, and then the integral of R squared is 1/3 R cubed, so 1/4 times 1/3 gives us 1/12. And there you have it. That's the electric potential at the center of this non-uniform spherical charge distribution. We can simplify that, I guess, a little bit. Say V is equal to C R squared over 12 epsilon naught times the quantity 2 minus R, whichever way looks simpler to you. Okay, now, if that's the case, and we know the electric potential at the surface is 0, what's the electric potential at some point out here? And what's the electric potential infinitely far away? If you want to solve for those, knock yourself out. I think you can find those fairly easily just by applying the general formula. The electric potential at any second point minus the electric potential at some other point is equal to negative the integral of path from 1 to 2 of E dot dr. So now that we know the electric field outside is just kq over r squared, you can use that to find the difference between the surface and this point C along with this general form. Okay, thanks for watching.